last time about rebalancing and so on? Can you hear me?
Yes, sir.
Huh. So if there are no questions, then let's talk about some sorting algorithms. So, so we'll talk about 4 algorithms today. Insertion sort, selection sort, merge sort, and quick sort. So before that, I want to do a quick recap of the asymptotic of the big O notation, correct? So when do we say that a function f of n is in order of g of n, which is also written somewhat misleadingly as fn is equal to order of g of n. When such that for all n greater than equal to n naught, fn is less than equal to c times g times n. Correct? So this is the definition. What does this mean? G of n is some function which grows somehow. So your fn is smaller than it eventually. And eventually means in terms of it's lesser than c times g of n. So if you draw some shifted version of this graph, fn is less than that eventually. So fn could be something like this. It's slowly growing. So you can take, if it's an increasing function, you can take this as n naught. And now it is actually lesser than this. And maybe it's not lesser than this. Maybe it's like this. Then you would just, yeah. So C can be adjusted, correct? So what that, for example, is equal to a function. So this is exact running time of your algorithm. Let's call this fn. Let's say 30 n squared plus 16 n plus 14. Then we say that fn is equal to order n squared. So because there exists c equal to 30, and there exists a large enough constant. In this case, it's I guess so there exists a constant, there exists not such that fn is less than cn squared, correct? Or let's say put c equal to 31 for good measure, correct? So because eventually this part will be less than n squared, and therefore this entire thing is less than 31 n squared. So the idea is, if you have a function f, so we'll usually be dealing with polynomials fn, usually polynomially bounded, can have log n factors like fn is equal to order n log n, which means that it lies somewhere between n and n squared. And so log n is a very slowly growing function, as you already know. log it's so it is something like this. We just have to worry about it goes to infinity but very slowly, correct? So it is the number of bits to represent n, roughly the number of bits to represent n. When we say log n in computer science, usually we mean log base 2. Log n is equal to log base 2 of n. And other logs are just a constant factor away. So this order notation does not matter. So basic idea is you drop all the negative. So you want to majorize it.
Sir, you weren't audible for some time.
Terms and the lower order terms.
Sir, you aren't audible anymore.
That will the exponent of that will give you the asymptotic dependence, the big O, correct? And usually when we talk about algorithms in a practical sense, then uh, uh, we are bound by uh, usual running time in the machines. So the operations that we assume are constant time operations um, so what are in a practical sense what are the number of operations that we can support a machine typical machine can support. I don't know whether this thing is dated or not, but something like 10 to the power 8 operations per second are definitely are achievable by usual computers, and 10 to the power 8 means that if you have a linear time operation, you can uh, so so let's draw a figure. So so in linear time 10 to the power 8 is possible. In if you have quadratic time, then you have so linear 10 to the power 8, quadratic 10 to the power 4, and cubic something like 10 to the power 3 is like something below 10 to the power 3, and n log n is something like so this is what is log of 10 to the power 8? It is 8 log 10, that is 8 threes are 24. So it is something like I don't know, 4 into 10 to the power 6, something like that, or the order 10 to the power 6. So these kind of operations are possible. for various complexities. Practically possible. So keep these kinds of things in mind when you actually attempt assignments, because rather than giving away the running time, we will tell you on what size inputs your algorithm will be measured. And of course, remember that there might be large constants involved which would kind of disturb the running time. So if you have a constant like 10 to the power 100, a so-called galactic constant, then even a linear time algorithm would take too long. Correct? But in practice, usually the constants are small, and therefore the asymptotic complexity is the most important thing. But nevertheless, just be aware there are algorithms which require galactic constants, even though their running time is asymptotically small. It's a linear time algorithms with constants which are like 10 to the power 100 before them, and so on. Correct? So so any questions so far? No. Are you there, by the way? Are people there?
Yes, sir.
Okay. So let's start with insertion sort. This is so we'll see the running time, it's order n squared. But so if I were to write, how would I write I sort on an array A is on a, let's say on a list A, then how would you write it? If A equal to the empty list, then return A return A0 plus I sort A A1 colon, correct? So, no, sorry, what am I writing? That is fine. So return insert A0 in I sort of 0 A0 colon 1 colon. A1 colon. Correct? And insert, we have not talked about insert, but insert just traverses the list, a list and a sorted list. So insert traverses a sorted list. So insert of what? Insert element E, comma A, and the first element which is A, then E after the E after the first element smaller than E. first element before the first element greater than E, correct? So basically, you are all we are doing is, if you have a list like 5, 6, 8, 2, 3, 9, you want to do this to sort this list. Keep 5 aside, sort this list. You get 2, 3, 6, 8, 9, and then you go to this list and find the first element which is greater than 5. So this is smaller, this is smaller. Insert 5 here. Correct? So you get 2, 3, 5, 6, 8, 9, correct? So what is the running time of this? Assuming, so what is the running time of this algorithm? So if you have no elements, then it takes order 1 time. And if you have n elements, then you have to first sort the remaining n minus 1. Then you have to traverse the list and spend basically at most n minus 1 time in shifting the rest of the elements. Correct? So when you do this, so assuming we are working with arrays, we would have to shift this here by 1. That takes at most n minus 1 time. And so this is a recurrence. How do we solve it? This is just Tn minus 2 plus n minus 2 plus n minus 1 is equal to so on and so forth. Tn minus 3 plus n minus, sorry, n minus 2, what am I writing? N minus 3 plus n minus 2 plus n minus 1 is equal to T0 plus 0 plus 1 plus n minus 1. T0 is 1. So this is equal to 1 plus n into n minus 1. N into, n into n minus 1 by 2. Correct? So which is, we can see that's equal to order n squared. Correct?
Yes, sir.
So so far, any questions? Then we do another sorting algorithm, selection sort. So this is kind of the dual of insertion sort. Instead of finding an element, instead of taking an element and placing it at the correct place in the sorted list, what you do is you find the smallest element, find the smallest element in the list, delete it from the list, and sort the remaining list, and and place. So your result is the element followed by the sorted list. And the smallest element E. Sort the remaining list to get S. Correct? So again, the running time is very similar. You require, so Tn, now you do first step is to find this element that takes n time plus sorting the rest of the elements takes tn minus 1 time. And this has a similar recurrence. It is n into n plus 1 by 2 is equal to order n squared. Correct? Are you with me?
Yes, sir.
Okay, so these are very simple things which you must have seen earlier, but nevertheless, let me do them for the sake of completeness. So, merge sort. So far, removed an element. In insertion sort, we took an element, removed it, and then so we took the first element, for example. We took the rest of the list, sorted it, then put the element in its correct place. Now, merge sort is similar to this. Only thing is that, so basically in insertion sort, we broke the list into two parts, one containing one element and the rest containing the remaining elements. And then we sorted the long list and we merged the two lists, the one element list and the n minus one element list, correct? Here in merge sort, we do something similar. The only thing is that we break the in of roughly equal size. I mean, if there are odd number, so roughly equal size, sort, merge sort each sub array recursively, and then the two to be more precise, how do we define merge sort? For a list L, let L1 be equal to merge sort of L1 colon len L by 2, and let's say this is floor, and let L2 be equal to merge sort of L1 colon len L by 2 plus 1 sorry, what am I writing? Colon, correct? Let's say this is 0. Correct? So we break it into two parts. And then we just return merge of merge sort of merge of just L1 and L2. Correct? So, and how do you define merge? So how do you define merge? Merge L1 and L2. So the recursive way is very simple to describe, but it's inefficient. But you can make it iterative easily. So what is the recursive way to do it? If L1. So firstly, if L1 equal to empty, return L2. If L2 equal to, else if L2 equal to empty, return L1. Else what do you do? Sorry. If L1 0, so now both the elements, both the lists have elements. Return L1 0 plus merge L1 1 colon comma L2, else return L2 0 plus merge L1 comma L2 1 colon. So is this clear? I mean, this is just a recursive implementation of merge, but you can do it iteratively. You can go through the list, keeping track of which has the smallest element and outputting one of the two elements under the pointer and advancing the pointer that contain the element that you have outputted. Am I clear?
Yes, sir.
Okay. So so now what is the complexity of this algorithm? So firstly, let us decide what is the complexity of merge L1 plus L2. So merge runs in time order length of L1 plus L2. Correct? Plus 1, let's say, for the constant, this thing. Even if both are 0, it will take order 1 time. Correct? Is this clear? Because T of 1 is 1, T of 0 is 1, and T of n is equal to 1 plus T of n minus 1. Order 1 plus Tn minus 1. So more formally, you can write that Tn is equal to C plus Tn minus 1 for some constant C, but C occurs throughout, and T0 takes time, some constant C. So you can even leave out, you can divide out throughout by C. So if you solve this, you would get this is equal to C times n, correct? Now if you divide out, so the other way to do is just to say that this is equal to 1, Tn is equal to 1 plus Tn minus 1, shifting everything by C, and this is equal to n, correct? So absorbing the constants inside the T, so we would get, so is it clear?
Yes, sir.
Okay, so merge runs in time order. So no, I was not precise enough. This is a so T of n1 comma n2 is what we have to write, right? L1 length of list L1 is n1, and length of list n2 is n2. So what is it? This is equal to 1 plus T n1 minus 1 comma n2 is the maximum of this, and T n1 comma n2 minus 1. Correct? Let's say less than equal to. So remember, so here I should mention that we are computing the worst case time, correct? This is the worst time that the algorithm can take, maximum number of running steps for the algorithm over all inputs, correct? So now this this recurrence you can guess has solution is less than n1 plus n2 plus 1, and then you can actually yeah, so this you can prove is less than n1 plus n2 plus 1, and so the simple equation that I wrote was for t of n1 comma when n1 and n2 were both n, then it takes order n time, correct? So let's call this t2. This one was, let's call it t2. So t2 n comma n is equal to 2n plus 1 is equal to order n, correct? And this is just t of n, correct? So either way, I mean, whichever way you see it, you can say that it is order n time, correct? Now, what is the time for merge sort? So merge sort, you do tn, you divide it into two parts, twice tn by 2, plus now you spend n time in the merge, correct? So this is equal to twice twice tn by 2 squared plus n by 2 plus n is equal to twice 2 squared tn by 2. I'm just rewriting this plus n plus n. This is again simplifying. You can simplify and see this is 2 cubed plus n plus n plus n, and so on. This is equal to 2 to the t times t n by 2 to the t plus t times n. Correct? We can prove this by induction. And putting t is equal to log n. So this is equal to 2 to the log n, t n by 2 to the log n plus n log n, and this is equal to n times t1, this is less than t1, plus n log n, which is just equal to order n log n. Correct? Are you with me?
Yes, sir.
Okay, so having said that, let's move on. But just one analogy is that in insertion sort, you took an element and so you broke the element into broke the list into two unequal parts, sorted both of them. Sorting one list is trivial, it's just one element long. Sorting the other list is more complicated, you do it recursively, and then you merge the two lists. You put the element wherever it belongs. In merge sort, we did exactly a similar thing, but the only thing is that we broke the list into two equal parts, and therefore we got a gain in the running time, correct? Now the question is, can we do a similar thing for selection sort?
Sir, so can you explain the last two steps of the previous?
Sorry?
So we can't see
Hello?
your screen.
Now can you see it? No.
No,
One
sir.
second. One second.
So can you explain the last two steps of the previous?
Just one second. One second. One second. I will do that. last two steps of from these two.
Yes, sir.
So by induction, you can prove that this Tn is equal to 2 to the T for 2 to the I if you want. I should have chosen a better variable name. So 2 to the I, n upon 2 to the I plus I times n. Correct? This you can observe or just prove by induction. Correct?
Yes, sir.
Now you put I is equal to log n. Correct? Now what is 2 to the log n? So I should say more formally, it is 2 to the it is floor of log n. So we will get floor of this, and floor of this. Okay, so now 2 to the floor log n is less than n is less than 2 to the floor of log n plus 1. Correct?
Yes, sir.
So now what is n upon 2 to the floor log n? It lies between 1, n upon 2 to the floor log n is less than 2. So you get this something which is less than, I wrote T1, but this is certainly less than T2, assuming that it's an increasing function of n, correct? So, I mean, to make it more precise, this is 2n lesser than T2, and this is just equal to 2n, meaning this is an order n function plus order n log n, which is equal to order n log n. Is it clear?
Yes.
So, and maybe I should have gone to ceiling, it would have been slightly easier. But anyway, I mean, does not matter. T2 is also a constant, T1 is also a constant, so it does not matter here. So selection sort. So in selection sort, yeah, so in selection sort, we choose the maximum element and then we insert it, then we so we choose the maximum element and we sort the rest of the list, correct? So we divide the, so basically I'm trying to motivate quick sort from selection sort, correct? So so you take an element which is the minimum element and keep it in the beginning of the thing, correct? Then you sort the rest of the array, and so merging doesn't take any time. Selection takes time, selecting the smallest element takes time, but there is no merge step. You don't have to insert the element in between, correct? Similarly, in quick sort, what you do is you have this array. You first say pick an element and divide the list into two parts. So that these are, suppose this is some element A, you divide the list into less than A and greater than A. Correct? And then you move A away and basically then you sort these two. Sort and sort. Correct? So if you do that, then then you would get a sorted list. And to sort this, you again pick an element A prime here and A double prime here, and you divide the list into two parts where you keep the things less than A prime here, greater than A prime here, and so on. Correct? So why is this quick sort related to selection sort? Because essentially we are dividing in selection sort is quick sort in which you pivot. This is called the pivot by the minimum element. So selection sort is quick sort with pivoting on the minimum element. So now this pivot, how do you choose? Ideally, you would like to break the array into half-half. But if the element you choose is the minimum or the maximum, then you know that the running time will be as bad as selection sort, which is order n squared. Correct? So one simple heuristic for choosing the pivot is the first element. Okay, you take this to be the pivot, call this the pivot, and then you divide the array into two parts, keep the elements which are less than A here, greater than A here, and then you exchange A with the boundary between them, the element at the boundary. Correct? So now the last element less than A. So this now, all of these now become less than A. This remains greater than A. Correct? Are you with me?
Yes, sir.
So, but there are cleverer ways of pivoting. But let us first analyze quicksort. So it will of course depend, unlike merge sort in which it's a deterministic algorithm run with the worst case running time of order n log n. The worst case time of quicksort is order n squared. Correct? If you pick a bad pivot. And what is a case in which quicksort is bad? Can somebody tell me what is a bad, assuming A0 is when the list is sorted? Yes. So when the list is sorted, you will find the pivot will not partition the list at all. So ideally, so if A1 is less than A2 is less than AN, then and you pivot by this, then you would have to sort this and you would pivot by this and so on till you reach AN. Correct? So it would take n calls, and every time you would have to scan the list to find the to verify that the pivot is indeed the smallest element, and so it takes order n squared. Correct? But what in the best case, what would happen? So best case time doesn't mean anything, but what is the best case? When pivot equipartitions the array. Meaning, that is, pivot is the median. Correct? So, so if you know an by 2, then you would pivot by it, and then you would then your so you would separate out the elements smaller than n by 2 on the left, the elements larger than n by 2 on the right, and then recurs. So again, the recursion would be Tn is equal to Tn by 2 twice Tn by 2 plus order n. Correct? In fact, it would be order n plus twice Tn by 2. N by 2 time to order n time to determine the median, and then twice Tn by 2 to merge sort, to quick sort each half. Correct? I have not yet told you how to partition the elements via the pivot, but we'll do it in a minute. But just let me mention one thing, that there are two ways of pivoting. One is a random. Pick from through n. Okay, so it's happening. So if you pick a index randomly from 1 through n, notice we are not randomizing over the, the order profile of the elements is not randomized. We are just randomizing over the choice of the pivot. Okay? So if we randomly choose choose a pivot from the n with high probability, it would partition the array not into half, but with high probability, it would partition them into parts which are each is at least n is equal, so which is greater than equal to c times n. And then you can see, so you would get Tn is equal to, so with high probability, you would get this is equal to Tn by 3 plus twice Tn by 2n by 3. I don't know what am I writing. T2n by 3 plus order n. So under this probabilistic assumption, with high probability, the expected running time, so ETN would be the expected running time of this would be something like would be equal to order n log n. Correct? So I have not made this precise, but a randomized pivot partitions the array into roughly equal parts with high probability, and this holds under expectation. Expected number of items which are smaller than this and larger than this are roughly equal, and then you can do this. Correct? The other way to do it is in a deterministic way. So there is a median find algorithm which finds basically an by 2 in order n time, deterministically. Correct? And while I will not go into the details of this algorithm, at least theoretically, this is very attractive. You can deterministically that why not merge sort? What are the advantages of merge sort over quick sort and vice versa? So merge sort is so let me do this on.
Sir,
Tell me.
so why was worst case time for quicksort O(n square n?
Because it degenerates to selection sort if you pick the pivot badly. If the pivot that you pick is smaller than all the elements at every step.
Okay, so it's just insertion, selection sort.
So then it's just selection sort.
Okay, fine. Thanks.
I'll do it in 5 minutes. But let me highlight the differences between merge sort and quick sort. So this is in place, and the other thing is stable. Correct? So in place means you do not need any extra array to any extra space to do the processing. But merge sort needs extra space. Quick sort, on the other hand, does not. So why does quick sort? Why is quick sort in place? Because at a high level, what you can do is you have this array, correct? You keep your pivot in the first square. So A0 is suppose the pivot. Now you divide your array into 3 parts. One is those which are less than A0, those which are greater than A0, let's say greater than equal to A0, and these are, the third part is untested. Correct? So initially the array will just look like A0, and your the left pointer would point here, and the right pointer would point here. Correct? So there are no elements which are, so the only element smaller than AZ, smaller than, let's change this thing. Say the small element smaller than equal to A0 are A0, are just the first element, and there are no elements which are larger than A0 node. Correct? Now at every step, you move your pointers rightwards, this left pointer rightwards, and the right pointer leftwards, till you find an element, the left pointer hits some element A. So till AL is, so these are all smaller than A0, and this is greater than A0. Correct? So you stop at the first point where AL is greater than A0, and similarly here you stop at the point where AR is less than A0. Correct? These are all properly, this is less than A0, and this is greater than A0. Correct? And now you just exchange these two. The things at L and R, you just exchange. You see my point? Hi, are you there?
Yes, sir, I did not understand it.
Okay. So what I'm saying is you maintain this invariant that all the elements are either untested or lie in the left region, which is left of a pointer L, or and are smaller than A0, smaller than equal to A0, or lie on the right of R and are greater than A0. Correct?
Yes, sir.
Now you start advancing R towards the right, while the elements are smaller than equal to A0. At some point, if the list is not sorted, you would find an element which is greater than A0. Correct? Correct?
Yeah.
So this would contradict your invariant. Correct?
Yes, sir.
This would be a bad element for in the invariant. Similarly, you move leftwards from R till you find an element which is less than A0. Correct? And if the list is not sorted, you will find such an element or reach, or both the pointers will meet. Correct? While the pointers are not met, you will find an element which is less than A0, and here it's greater than A0. And then you can just exchange these two. And then this invariant is met. Correct?
Yes.
So, and the untested region has decreased by 2. Correct? And throughout this process, you have never seen an element more than once. Correct?
So could you repeat that last point?
The last point is you have never compared an element more than once in this process. You are increasing L and checking whether AL is less than A0. While you see AL is less than A0, you increase your L. Similarly, and you stop when AL is greater than A0. Correct? Having gone over the intervening region, doing one comparison per index. And similarly for AR. And then you just exchange the two. Correct? So basically, why I'm doing this is because in order n steps in place, I can do the partitioning.
Sir, what will be the next pivot?
So after I've done this, I will look at this array and choose a pivot here. I mean, not this array, but meaning when we complete it, we would have run through the entire list. So it would be divided into 2 parts. And we would just run the algorithm on these 2 parts. Don't even need to exchange because A0 is less than equal to A0, correct? Or we can do this, correct? I mean, so we can do you see my point? So the pivoting strategy is separate from the partitioning, the way of partitioning, from the partition. So it could be randomized, or you could do a deterministic median find algorithm and determine the pivot. Correct? Are you with me?
Yes, sir.
So is it clear that this algorithm is in place? We don't need more than constantly many pointers, namely L, R, to store any extra items. So it is in place. Correct?
What do you mean by in place exactly?
In place meaning, apart from the given array, I don't need any extra storage except for constantly many pointers, constantly many extra space. I can work with the array plus constantly much extra space. In merge sort, if you see, on the other hand, I have to copy the so here I merge, do L1 and L2. I have to copy the list into, we I have to create two new lists and then merge them. So it's not in place. If you try to do it in place, things will go all right.
Yeah,
See my
okay.
point?
Yeah.
So you have to, yeah. So that is an advantage of quicksort. And with randomized, so I should say running time. Running time constant. So this is small and not so small. Meaning this constant for randomized, in the randomized case, this constant is very small. Correct? In the deterministic case, the constant is high, but that is a price you pay for doing a deterministic algorithm. Correct? So the other metric in which merge sort is better is that it's a stable sort. What does stable sort mean? That here we have said we had in mind an algorithm where all the elements are distinct, but that's not necessarily the case. In fact, we never assume that explicitly. It could be that there are many elements which are the same, correct? In an array, in a list, correct? Do you agree in principle that there could be many equal elements in a list, and now when you sort them, these equal elements will come together, correct? For example, if you have 1, 3, 5, 1, 2, 3, 4, correct? Then what will be the sorted list? 1, 1, 3, 3, 4, 5, correct? So these ones come together, these threes come together, this 4 and 5. So 4 and 5 are, of course, different numbers. So yeah. On the other hand, we could also have a list of these could be numbers, or it could be some records or some larger objects which you are sorting on the basis of some value, correct? So this one could be the value of an object, okay? The key value of an object. Not key value because there are multiple this thing. So basically you have objects O1, O2, OK, On, correct? And these are associated with values, correct? So val of OI. So, okay. So having said that, we want that basically if val of OI is less than val of OJ, then we want, so we want to sort on the values, correct? But if val of OI is equal to OJ, value of OJ, O sub j, then OI should come before OJ. In the sorted order, in a stable sorted order. So what is a practical example of this? Suppose you have a list of names and marks, correct? And you are, or you have a list of names and marks, and you are sorting on the basis of marks, correct? Now you want that, so suppose initially the list was sorted in alphabetical order on the names. After the sorting, you want that amongst the people getting the same marks, the list should remain sorted in alphabetical order on the names, correct? If that is the case, then it's called a stable sorting algorithm. Basically, the order that is there before the For equal objects, ties are broken according to the previous order. Am I clear, or is there confusion about this?
Sir, it's clear, sir.
Is clear. Okay. So merge sort implemented correctly is stable. Why is it stable? Because what do I mean by correct implementation? So let's see merge sort. So when you merge two lists, you want the list with the, so if L1, so what happens when L10 is equal to L20? You don't want to swap the values of L1 and L2, correct? So that's why you write L10 less than equal to L20, less than equal to L20, then you first apply L10, and then only you would do for L20, correct? So this equality means that this less than equal to means that merge sort is stable. On the other hand, if we made this strict and the other one non-strict, then it would not be stable, correct? So a good implementation of merge sort will make it stable. On the other hand, a quick sort is not stable. Why not? Because you are making large jumps in so you are comparing elements across great distances. See, an element here and here, you might swap them. So this is over great distances, and this leads to instability, correct? Why does it lead to instability? Because so anyone, why does it lead to instability?
There could be a case where, like, suppose like our pivot is smaller than this pair of alike elements. One is close to the beginning of the list and one is close to the end of the list. And there is a small element after the second one. So our pointers would hit these two elements and they would swap. So we've swapped the relative order of the two pairs.
Yes. Yes. So we might swap the relative order of two things which are equal, and that leads to instability. So there is a trade-off even in these very simple algorithms. It's just to illustrate this fact, correct? Now I explained one way of partitioning. So this is the partitioning algorithm. And this is originally by CAR from the 60s. There is another very simple way of doing things where you maintain three lists, A0. So three parts to the list again. This is less than or equal to A0. This is greater than A0. And this is untested. Correct? Now, when you look at this, you will either put it here in the beginning of this list, or you would leave it here and advance this pointer. Correct? You see my point? So if this element x, if x is less than or equal to A0, then you would swap it with the first element in greater than A0. Correct? You swap these two. And if x is greater than A0, then you just advance this pointer. Correct? So again, you are maintaining two boundaries, one here and one here. And there is less swapping in this. I don't know. I mean, no. So not really. So these are roughly equivalent ways of doing things, but in practice, you can also do this. So is it clear?
Sir, could you repeat the last algorithm?
Okay. So you start out with an array containing the pivot in the first spot as usual, with 2 pointers, both of them pointing to this, correct? And this is your untested region. Now, at any point of time, you would have 3 regions, one to the left of this pointer, one to the left of this pointer, and the rest is untested, correct? Now you look at the first element after this, correct? If this element is smaller than A0, you have to put it to the left of this pointer, correct? So you swap the element here with this element and advance this to the right.
Yes, sir. Yes.
And if this is already larger than A0, then you just advance this to the right. So this pointer advances to the right one at a time. And in some of the cases, you swap the element that you discovered with the last element, with the first element of the greater than thing. And yeah, so it's very similar to the previous algorithm, but yeah, correct. So now questions.
Sir, I don't quite get how we will apply our algorithm recursively in place for quicksort, sir.
So which is the part that is not clear to you?
Sir, I get how we do make our partition, but after we do that, we need to recursively sort the 2 subarrays.
Yes.
I
yes.
don't get
So
how
you
we do
will-
that in place.
So you would again choose a pivot somewhere, whatever your pivoting strategy is. For example, if it's randomized, you would choose a pivot somewhere here, swap the pivot with the first element in this, and then do the quick sort on this part, with the pivot being in the first element. Similarly, in the second part, you would choose a pivot in this part and move it to the front of the list, front of this list.
Okay, I think I see it now, sir. Thank you.
So there are 2 parts. Yeah, correct. And yeah, so you denote the array by just the endpoints in between which you are sorting and the position of the pivot. And
Okay.
once you are done with the list, you choose a new pivot in the list and swap. So.
Okay, so sir, when we write the function for this, it would need parameters for start and endpoints of the pivot, right?
It would
not the pivot,
need for the yes, for the intervals.
Okay, and then when we recurse, we call it with different pointers and different start and endpoints. And
yes.
Okay, got it now, sir. Thank you.
So you could have a pointer for the pivot and for the endpoint of the list. And assuming that the pivot is the first element in the list, now you maintain these 2 pointers and advance them, however, till you are done, and then you,
Yes, sir. Got it, sir.
Okay. More questions? If there are no more questions, then let's stop here. And yeah. Yeah. So thanks. Have a nice day.
Thank you so much.
Thank you, sir.
Thank you.